All right, welcome to The Explainer. Today we're diving headfirst into a theory that, honestly, might just change how you see, well, everything. It's called single point theory, and it asks a wild question. What if reality, all of it, is just a good enough agreement? To get our heads around this, we're going to start with a pretty strange puzzle.
So let's just let that sink in for a second. What on earth could the number 28 possibly have in common with a hydrogen atom? I mean, on the surface, that sounds like a nonsense question, right? One is just a number, an abstract idea from math. The other is a physical thing, a building block of the very matter we're made of. But according to single-point theory, there's a deep, beautiful connection hiding in plain sight. And to see it, we first have to figure out what makes a number like 28 so special to begin with.
You see, 28 isn't just any old number. It's what mathematicians call a perfect number. And the definition is actually pretty simple. A number is perfect if it's exactly equal to the sum of all the numbers that divide into it, not counting itself. So take the number 6. What divides into 6? You've got 1, 2, and 3. Add them up. 1 plus 2 plus 3 equals 6. Boom. Perfect. It works for 28 too. Its divisors are 1, 2, 4, 7, and 14. Add those together, you get 28. It's a neat mathematical party trick for sure. But what does it have to do with physics? Well, this is where single-point theory, or SPT, comes in. It looks at these perfect numbers and sees something much deeper than a curiosity. It sees them as resonance signatures. Think of them as nature's blueprints for stability. Each number represents a kind of perfect harmony, a configuration where all the parts just click into place and reinforce each other. For the number 6, it's a simple 1, 2, 3 resonance. For 28, it's a more complex harmonic lock. These numbers, the theory says, are the signatures of things that last.
And this is where the theory gets really ambitious. SPT isn't just trying to explain one little corner of the universe, it's proposing that everything, every particle, every force, all the laws of physics we know, they all bubble up from one single fundamental process. It's an attempt to literally build the cosmos from scratch, from first principles.
So what is this process? At the absolute bedrock of reality, SPT says there's a primary cycle. Just imagine a cosmic metronome ticking away at a speed that is, frankly, impossible to wrap your head around. It's vibrating at 1.854 times 10 to the 43rd times per second. This isn't just fast, it's the fundamental frequency, the ultimate heartbeat that drives the entire universe into existence. And all that vibrating generates something called the process field. You can think of this field as the very fabric of reality, the stuff that everything is made of. It's a complex field, which is just a fancy way of saying it has two parts, two key components that work together to create everything we see and experience.
And these two components are amplitude and phase. Think of it like this. Amplitude is the substance of the field. It's the height of the wave. When the amplitude changes from place to place, it creates curvature, which we experience as gravity. Phase, on the other hand, is the twist. It's where you are in the wave's cycle. When the phase changes, you get flow and momentum. You get forces and moving particles. So gravity and forces, they're just two different faces of the same underlying field.
Okay, so this gives us a kind of recipe for reality. You start with that primary cycle, vibrating like crazy. This churns up the process field, creating tiny little whirlpools or vortices. Now, most of these are unstable. They just fizzle out. But some, the ones that find a stable, resonant, phase-locked pattern, they persist. And what are these stable, persistent vortices? They're the particles we know and love, like electrons. And all the laws of physics? They're simply the rules that describe how these stable little whirlpools bump into each other. Now, this whole idea forces a huge philosophical shift, which is captured perfectly in this quote. We tend to think of math as the source of truth, right? Like the laws of physics are written in some cosmic textbook. But SPT says, no, you've got it backwards. Math doesn't create reality. It's just the language we use to describe the patterns that happen to be stable and coherent enough to stick around. Mathematics is the grammar of reality's story. It's not the author.
And this leads us to the absolute core of the whole theory. The universe isn't built on some kind of razor's edge absolute perfection. It's built on something way more practical. Good enough agreements. The theory calls them nominal agreements. Stability, the very existence of things, doesn't require absolute infinite precision. It just needs things to be close enough to work.
Let's circle back to our perfect numbers to see what this really means. The classical view is rigid. A number is perfect if this equation is exactly true. But the SPT view is more flexible, more real-world. It replaces that rigid equal sign with a stability window, that little delta symbol there. All it's saying is that as long as you're close enough, as long as you're inside that little window of tolerance, the system is stable. It's physically perfect, even if it's not mathematically infinitely perfect. And this isn't just some theory. You can look up in the sky and see it happening. 3 of Jupiter's biggest moons, Io, Europa, and Ganymede, are locked in this incredible orbital dance. For every one time Ganymede goes around, Europa goes around twice, and Io goes around 4 times. But is it exactly a 1 to 2 to 4 ratio? Nope, it's off by about 1%. But it's close enough. It's within the stability window, and that good enough agreement has kept them locked in that stable dance for billions of years.
So what this really means is that our whole idea of perfection gets flipped on its head. Perfection isn't some absolute universal property. It's relative. It's a relationship. A system, whether it's an atom or a solar system, is perfect or stable if its numbers, its ratios, fall within that specific system's tolerance for error and noise. What's good enough for planets is different from what's good enough for particles.
Okay, so now let's look at how this one simple, powerful idea, this concept of good enough agreement, could be the key to unifying all the physics, from the smallest atom to the largest galaxy.
Because the theory claims this isn't just a one-trick pony. This principle of resonant good enough stability is the engine running the show everywhere. It applies at the quantum level, the atomic level, at the scale of Einstein's relativity, and all the way up to the cosmic web of galaxies. It's one idea to rule them all.
Let's get specific. Down at the quantum scale, why does an electron stick to its orbit in an atom? According to SPT, it's not some arbitrary rule. It's because that electron, which is just a vortex, has found a resonant, stable, phase-locked state. It has reached a good enough agreement with the field of the nucleus, and so it stays put.
Now, let's zoom all the way out to the cosmic scale. Gravity, in this picture, isn't some strange force pulling things together. It's just what the curvature of the process field's amplitude looks like on a grand scale. Big things like stars and planets make big dents in the field's substance, and other things follow those curves. So both the weirdness of quantum mechanics and the grandeur of gravity can emerge from the very same field.
And this, right here, is the beautiful, unifying payoff. The very same principle, finding a stable, resonant state that's good enough, is what keeps an electron in its place and what keeps Jupiter's moons in theirs. The micro and macro worlds aren't just connected, they're reflections of the exact same underlying physics of coherence.
Okay, this is all mind-bending stuff. It sounds elegant, it sounds beautiful, but is it science? Any theory worth its salt has to be testable. It has to make predictions that could potentially be proven wrong. So the big question is SPT falsifiable?
And the answer is a resounding yes. In fact, it makes some incredibly bold make-or-break predictions. For starters, it claims it can explain why galaxies spin the way they do without inventing something like dark matter. That's huge. It predicts tiny differences from standard quantum theory in heavy atoms that we could actually measure. It even says we should be able to take a special kind of laser and literally stamp a vortex structure onto an electron.
And here's a really clear-cut one. If you smash heavy ions together to create incredibly strong electric fields, our current best theory, QED, predicts you'll get a certain, very low number of positron particles. But SPT, because of its vortex model, says, nope, you're going to get a lot more, and the number you get will grow in a totally different way as the field gets stronger. This isn't a subtle difference. It's a clear experimental showdown. You run the test, you count the particles, and one theory is right and the other is wrong.
And that's what makes this so exciting. These aren't just minor philosophical points. These are real, high-stakes experiments that we can do with technology that exists now or is just around the corner. We could get data in the next decade that could either blow the doors wide open for SPT or send it straight back to the drawing board. That's how real science works.
So, we'll end with this final thought. Single-point theory presents this incredible, unified picture of a universe built on resonance and agreement. But maybe its most profound lesson is about us. If the universe itself is built not on absolute, rigid truths, but on contextual, good enough agreements, well, what does that say about our own science, our own knowledge? Maybe our theories are just that too, nominal agreements, the best possible models we can build, working within our own tolerance for error, always getting closer to reality, but maybe never touching some final, absolute truth. That is something to chew on. Thanks for joining us.